Welcome friends to the Formula Engineering classroom, and in this lecture we will try to understand the concept of different types of flow, or how can we analyze that kind of flow that is defined as flow patterns, linear and angular deformation, rotation, and so many other things. But this topic or this lecture I will start from a numerical that is completely based on our previous lecture. In that lecture we drive the concept of acceleration of fluid flow. Okay, so in that case that I'm starting this lecture by a numerical here. So in this numerical we want to drive an expression for acceleration through a nozzle. Means, let's suppose if I'm saying there is a nozzle here, that I'm saying this is a nozzle length, and in this case we want to drive an expression for the acceleration. Okay, so let I'm saying the flow through this nozzle, that we are considering this is the flow through this nozzle, we are specifying here this flow through this nozzle. I'm saying one dimensional, this is one dimensional flow that I'm saying, and this flow is also steady flow, this is steady flow. Okay, so we are saying that the flow through this nozzle is one dimensional steady flow, and I'm saying in this case the velocity is the only function of x direction, that is the only function of length here. Means I'm saying that is v is only function of x here. Means the velocity is not variable in this case with the y direction and with the z direction. This is my consideration. So let's first write our equations of acceleration that we drive in the last lecture. So let I'm writing ax, acceleration x direction. So we are saying this is u del u by del x plus v del u by del y plus w del u by del z plus del u by del t. So this is the acceleration in x direction, and as I'm saying in this case the velocity is the only function of x and this is not variable in y and z direction. That's why I'm saying ay in this case is 0 because there is no acceleration in y direction. Also az in this case is also 0 here. Okay, but now in this case, as we are saying velocity is not the function of x and y, sorry, that is y and z, so obviously this term, that is v del u upon del y and w del u upon del z, are also going to be 0 in this case because velocity is not the function of y and z. Also one more term here, we are saying the flow is steady. So when the flow is steady flow, in that case the variation of flow parameter with respect to time is going to be 0. Means there is no variation of flow parameters with respect to time. So obviously in this case the term del u by del t is also going to be 0 here. Okay, because the flow is steady. So our final expression that becomes ax is equals to u del u by del x. Okay, this is our acceleration under these stated conditions. Okay, now that I'm providing some boundary conditions here, that I'm saying at the nozzle base, means here at this section at the nozzle base I'm saying velocity is let v naught, this velocity is v naught here, and at the nozzle tip let we are saying velocity is 3v naught. Okay, these are our boundary conditions, that is we know this thing. Now so as velocity is only function of x and this is the linear function, in that case I think we can say that is v is equals to ax plus b. Okay, velocity is the linear function of x only. So here we have two constants a and b. So first we have to find out these two constants. Obviously to find out these two constants we require two boundary conditions. So I think we have two boundary conditions here, that is at x equals to 0 the velocity is v naught, and at x equals to L the velocity is 3v naught. Okay, so we have three boundary conditions here. So let I'm applying the first one, and let I'm saying at x equals to 0 v, that is velocity, is going to be v naught here. So by using this boundary condition you can say here as x is going to be 0 and v is going to be v naught, in that case the b become the V naught here. So from here we can write B is equals to V naught here. Okay. Now second boundary condition we are saying at x equals to L, V is equals to 3V naught. Okay. So let's apply this boundary condition. So obviously we know what is B is V naught here, and at x equals to L, V is going to be 3V naught. So I'm saying V is going to be 3V naught as x become L and B is V naught here. So from here we can calculate the value of A here. So I think this value become 2V naught by L. 2V naught by L. Okay, so this is the value of A here and this is the value of B here. So now our expression, that is V equals to AX plus B, becomes, so we can write this is V equals to, so the value of A is 2V naught by L into X plus B. B is V naught, so we can write this one, or we can rewrite this one and we can take V naught common here and we can write this is 1 plus this is 2x by L. Okay, so this is how our velocity is varying with respect to x here. So velocity is the linear function of x here, but we want to drive an expression for the acceleration, and we know our acceleration ax is equals to u del u by del x. So now here u is the velocity in x direction only, that we are defining our v. So for this one we can write as ax is equals to u del u by del x. So our u is this one, v. There is some function of x here, so I can write ax. Ax is equals to, first I am writing u is v naught 1 plus 2x divided by L, and this is multiplied by the partial derivative of this velocity with respect to x. So this is the partial derivative of u is, that I am writing v naught 1 plus 2x by L. Okay, now so this remains same here because this is u here, so we can write this is v naught 1 plus 2x by L. Okay, now over differentiating this one, so this is a constant term and we are differentiating with respect to x here, so this is constant, so this is going to be 0, and when we are differentiating this quantity with respect to x, we are only getting 2 by L here. Okay, so by differentiating this term we are only getting what, this is v naught, so we are getting 2 v naught by L here. We are getting this is 2 v naught by L here. Okay, so from here let I'm writing this expression here, so ax becomes, so I'm multiplying, this is 2 v naught, so I'm writing 2 v naught square by L. I'm simply multiplying this one, and in bracket the term is going to be 1 plus 2x by L here. So this is our expression of acceleration through this nozzle under the given conditions. Okay, now let's suppose you want to calculate what is the acceleration at the nozzle base. Okay, so at the nozzle base the condition is what? The condition is that there is x is equals to 0 here. So we are saying acceleration at nozzle base. So in this case x is going to be 0 here, so this whole term is going to be 0. So only remaining term is what? This is 2 v naught square by L. Okay, I am saying this condition when x equals to 0. And let you want to calculate acceleration at the nozzle tip. So you can say that there is acceleration at the nozzle tip. So obviously at the nozzle tip x become L. So we'll put the value of x here, that will be L here. So L is cancelled by L1. So this L is cancelled by L here. It become 1. So that is 2 here. So 1 plus 2 is 3 become here. And this 3 is multiplied to this quantity, it becomes 6 v naught square by L here. So this becomes 6 v naught square by L here. So this is the acceleration, and we are defining that x equals to L at the nozzle tip here. Okay, so I think point is clear. Now if let's suppose the flow is given 2-dimensional, so in that 2-dimensional case only Az is going to be 0, but there is some value of ay here, so in that case you have to calculate ay also. In this case, if the flow is given three-dimensional, in that case there is no term that is ax, ay and az is not going to be 0. We have to calculate all three terms. If the flow is defined as unsteady flow, in that case this term that is del u by del t and the term in ay that is del v by del t and the term in az that is del w by del t are not going to be 0. In that case we have to calculate all the terms of acceleration in x, y and z direction, and then we have to do some vector sum to find out the final value. Okay, so I think the point is clear. Now we will discuss the different type of flow, and this is important to discuss this here because when we will discuss the next topic of fluid mechanics, in that case we required the information of this type of flow, and on basis of this one we will drive the theories and we will discuss numericals, and that's why we are discussing this one. Like we can say that is different type flow means what? Means simply in this case when the fluid is flowing, in that case it is showing different category, and that's why we have to categorize this one. So we are starting from our type of flow topic, and we will start with the laminar and turbulent flow. Okay, so first we are discussing laminar and turbulent flow. Turbulent flow. Okay, so first we will try to understand what is laminar flow. So let's consider a pipe here or at two plates, and we are considering two stations here. This is station 1 and this is station 2. Now due to the viscous nature of fluid, the fluid will try to flow in layers. Actually the term lamina means layer. So when the fluid is flowing in layers like this, then we are defining the fluid flow is laminar flow, and in this case the layer are not going to be intermixed and it is moving in the straight path here. Okay, that's why we are also defining this type of flow is a viscous flow. Means laminar flow is also defined as viscous flow because this is due to the viscous behavior of fluid. Also it is defined as streamlined flow because in this case the layer are not going to be intermixed here. So whenever the fluid is flowing in layers, then we will say that flow is laminar flow or viscous flow or streamlined flow. But if let's suppose again I'm considering these two plates, station I'm considering 1 and station 2 here, and let's suppose in this case the fluid is not flowing in layers. In this case the fluid layers are going to be intermixed here. I'm using the word layers intermixing, but in this case intermixing is happening here. So when this intermixing will happen here, in that case we will define the flow is going to be turbulent here. And for the turbulent flow there is one more term is used, that is when the turbulent flow is happening, in that case we can define that is there is some transverse velocity or transverse fluctuating velocity happen in this case. What is the sense of transverse fluctuating velocities? Look at the laminar flow. In this case let's suppose there is a particle here and this particle is moving in the straight path here, and if we are considering this is the longitudinal axis here or pipe axis here, pipe center line here, in that case this particle is not moving up and down motion here. That is, this is not moving in the transverse direction here. If you are considering this is longitudinal direction, so this is transverse direction. But in case of turbulent flow, this particle is moving along this line, but it is also showing some up and down motion, that it is when moving, that it is here, now it's when moving in the upward direction and it's going to be down here, similar in these velocities or these layers. So in their case there is transverse velocity or fluctuating velocity is happening here, and in this case there is an intermixing take place. So this type of flow pattern is defined as turbulent flow. Okay, and this is defined as laminar flow. I'm discussing all these types of flow in short here, but in next chapter we will deal with it in details here there. So this is our laminar flow and this is our turbulent flow. Now second category we can define, let's suppose I'm making line here. Second category I'm defining here, steady and unsteady flow. Steady and unsteady flow here. Okay, this is our second category. So when we are using the word steady flow, so this term is especially related to the time. Means a flow is termed as steady flow when the flow parameters are not varying with time. So let's suppose if I'm considering a velocity. Okay, velocity I'm considering a flow parameter. I'm saying this is a flow parameter. Now if I'm saying the flow is steady, so if I'm saying flow is steady, in that case this velocity will not vary with respect to time. There is no change of this velocity with respect to time. Means over the time intervals the velocity remains same. So if there is no variation of flow parameters over the time interval, then we will define the flow as steady flow. Okay. Now second, let if I'm saying the flow is unsteady flow, if I'm saying unsteady flow, in that case the flow parameters will vary with respect to time. Means in that case the parameter will change over the time interval. Means let's suppose we are saying at the time t equals to 1 the velocity is some let 2 meter per second, but maybe at time t equals to 5 the velocity is going to be 10 meter per second. So velocity is varying with respect to time in case of unsteady flow. So when there is mentioned that this flow is unsteady, in that case the flow parameters are varying with respect to time, but in case of steady flow the flow parameters are not varying with respect to time here. Okay, so point is clear. Now next category, and I'm defining our third category, I'm saying uniform and non-uniform flow. So I'm saying this is uniform and non-uniform flow. Non-uniform flow. So as I defined steady and unsteady flow based on time, uniform and non-uniform flow is based on space parameters. Means it is based on x, y and z. Okay, as the steady and unsteady flow is based on time, here we are defining that is uniform and non-uniform flow is based on space parameters. So if we are saying some flow is uniform flow, some flow is uniform flow, in that case the flow parameters are not the function of space parameters. Okay, this is sorry, I'm defining this is wrong. It is actually equals to 0. It is not equals to 0 in this case. Also uniform flow, the change of flow parameter with respect to space is 0. I defined here wrongly. Here the velocity, there is no change with respect to time here, but there is changes with respect to time here. So in case of uniform flow, the flow parameters are varying with respect to, not varying with respect to space here. So what is the sense of this one? That is the flow parameters are not varying with the space. So let's take an example here, that I'm saying there is a pipe, let's suppose we are considering, and some fluid is flowing. Okay, some fluid is flowing here. Obviously here I'm considering laminar flow. So some fluid is flowing over here. Now let me consider this is the direction of flow here. Now if there is no viscosity, first of all we can't say this one, but let's suppose we are saying that if there is no viscosity, means the flow is fluid is ideal fluid in this case. So in that case there is no slip condition here. Okay, if I'm saying the fluid is ideal, then there is no slip condition. So means if there is no slip condition here, then there is no variation of velocity over this cross section. Okay, second point, as we can see here, the cross section of this pipe or duct is constant, means it is not variable, it is uniform. So in this case, the velocity is also not varying in the flow direction. Means in this case, the velocity is not varying with respect to space coordinate. So this type of flow is defined as uniform flow. Okay, let if I'm making a cross section here, and if we are taking a visualization or velocity distribution pattern here, when we are saying the fluid is ideal, so in that case, over the cross section there is no variation in velocity. The velocity is throughout same. This is not the function of y here. Let if I'm saying this is y here, this is y here, this is x here. So velocity is not moving in x direction, because when you check, if this is our station 1 and this is our station 2 here, and when you will check the velocity here, it will also show the same value. So in this case, the velocity is not varying with respect to x, the velocity is not varying with respect to y. So this type of flow is defined as uniform flow. But practically this is not possible. Why? Let we are saying the flow is non-uniform flow. So we are saying non-uniform flow. Non-uniform. Okay. This is non-uniform flow. Okay. So in this case, the flow parameters are varying with respect to space coordinates. Means the change is not zero, there is some change. So when the flow parameters are varying with the space coordinate, the flow is termed as non-uniform flow. Like that, again I'm taking this duct here or pipe here, and we know there is no fluid which has zero viscosity in real conditions. Okay, so if we are taking the two stations here, station 1 and station 2, let's suppose we are saying station 1 and station 2, and there is some flow here. Again I'm taking the laminar flow here. So obviously when there is some viscosity, and I'm saying this is the flow direction, so when there is some viscosity, then there is no slip condition here at the boundaries. So we can say this one, this is no slip condition here. So when the no slip condition is here, in this case the fluid layer stick to the solid surface has zero velocity at this surface, also at this surface, but the fluid layer which is at the center line has the maximum velocity. Means there is some velocity gradient over the cross section, and it will look like this one. We can say it will look like this one. This is the velocity distribution. Means at the solid surface the velocity is zero, but at the center line or at the center of pipe or duct the velocity is maximum here. So you can see this one, there is a variation of velocity over the y coordinate, but as the pipe cross section or the duct cross section is uniform, in that case there is no change in velocity in the x direction. Means when you will check at this station, you will see the same profile here. So there is no velocity variation over the x, but there is some velocity variation over the y. So if you are considering this one in 3D space system, so in 3D space system there will be some variation of velocity over the z dimension also, because there is side by side wall conditions here. So at the wall the velocity is going to be 0, and at the center the velocity is going to be max here. So means practically uniformity can't be achieved, because the flow is not ideal, so the fluid is not ideal. In that case there will always be change in the flow parameters. So practically uniformity can't be achievable. So this is our non-uniform flow. Okay, so I think the point is clear. Next we are defining rotational and irrotational flow. Let if I am considering fourth here. So we are defining rotational and rotational flow here. Okay, so this is a rotational and irrotational flow here. So what is the sense of rotational and irrotational flow? So let's consider this one. Let's suppose this is the line along which the fluid is moving, or fluid particles are moving. So let we are considering a fluid particle over here. Okay, this is our fluid particle, and this fluid particle is over this line, and this is the center of mass of this fluid particle. Okay, I'm indicating by some different colors, but I'm saying this is the center of mass of this fluid particle. Right now it is here. But when it move from this position to some another position, in that case, let's suppose if I'm saying it is here, in that case the position of this one, of this fluid particle, will look like this one. Means this is the center of rotation here. So you can see here, when it's moving along this line, it is rotating. Okay, when it's moving along this line, it is rotating. Means when it's move further, it will look like this one, and further it will look like this one. Means when it's moving, it's rotating about its own center of mass. This is the center of mass of this particle. So we can provide a definition for the rotational flow. We can say that a flow is said to be rotational flow when the fluid particles are rotating about its own center of mass during the flow. Okay, I'm repeating again. A flow is said to be rotational flow when the fluid particles are rotating about its own center of mass during the flow. So this type of flow is defined as rotational flow. We are defining this is rotational flow. Rotational flow. So what is irrotational flow? Obviously, when the particles are moving along a line, in that case they are not rotating about its own center of mass. Means this is our particle, it is here in this position. Okay, next position, this one, means they are not rotating about its own center of mass when they are moving along the line. So this type of flow means we can say that is when the fluid particles are not rotating about its own center of mass during the flow, then that type of flow is defined as irrotational flow. So we can say that this is irrotational flow. Okay, so I think the point is clear. In next category, we are defining compressible and incompressible flow. So when we are saying flow is compressible, when we are saying the flow is compressible flow, so we are defining compressible flow based on the density of this one. Means if the flow density is going to change, then we are defining the flow is compressible flow. Means we are saying that is change in density is not equals to 0. In that case we are saying that is density is going to change, then the flow is defined as compressible flow. Similarly, when we are saying the flow is incompressible, then the density of flow is not going to change. Means in that case we are saying the density of flow remains constant. So through this one we can define the flow is compressible or incompressible. Or in next category we can define the pressure flow and pressureless flow. Pressureless flow. Okay, so what is the sense of pressure flow? So let's suppose there is a pipe. This is a pipe wall here, and in this case flow is happening and pipe is completely filled with the fluid. In that case means we can say that is, in this case there is no free surface of fluid in the pipe. So in this type of flow, or simply we can say that this type of flow is defined as pressure flow. Means we can say that if there is no free surface of flow is happening, or if there is no free surface at all, in that case the flow is termed as pressure flow. So this type of flow is defined as pressure flow. But let's suppose if we are saying some river is flowing. So this is the solid surface over which river is flowing. So in that case the river is maintaining the free surface. Here is the free surface. Okay, here is the free surface. So when there is free surface, then that is defined as pressureless flow. Or you can say that if there is a pipe, but the pipe is not completely filled with the fluid, but there is partial, or the pipe is partially filled with the fluid, in that case also this is also free surface over here, then this type of flow is also defined as pressureless flow. Okay, so when there is no free surface, then the flow is pressure flow, and when there is pressure, or when there is free surface, then the flow is pressureless flow. There are so many other categories of flow, but this is sufficient for us for getting them in next lectures. And guys, please like the lectures, subscribe the channels, comment your doubts, and share the knowledge as much as you can. Hope you like the lecture. See you in the next lecture. Till then, take care of yourself, and thanks for watching. See you soon.